Everybody okay on these terms right here? Octal numbering system. What's the base of octal number system? Oh, y'all got that right. I think everybody got that. What's the base? 8. Good. Yeah. And hexadecimal base. Hex is 6, decimal's 10, so that tells you the base. So this is the numbers that's available in the octal number system. So you'll never see a digit. If you see something that's greater than 7, you know right off the bat it's not octal. So the largest digit available in the octal number system is 7. So if I was going to count in octal, what would we do? We're going to start off with 0. We'd go what? 0, 1, 2, 3, 4, 5, 6, 7. What comes next? 1, 0. And like I said, 1, 0 is always the base. And then I'd go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. What would come next? 2, 0. There's no such thing as 1, 8, right? And I know it's hard because in your brain you're thinking what? You're thinking decimal. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 3, 0. Good, yeah. So this is the way we count. It says that's weird, right? From an octal number to binary, says form an octal number from a binary number by grouping the binary number in groups of what? 3. 2 to the third. How many combinations is 2 to the third? Look on your chart. 8. How many combinations does each digit of octal have? It has 8. So they match, right? As long as they match, then we can go between the two numbers. 3 bits of binary for every octal digit. Now, why we're doing this, because PLCs, every PLC that I've dealt with still supports this. Even though hexadecimal is a lot more efficient because we can represent bigger binary numbers with fewer digits. This was the first base that we used in computers. So what we would do is we would come up here and we would just take a big, large binary number. So hexadecimal, we take the binary number and split it into groups of 4, right? Octal, we split it into groups of 3. So what would we do? We'd come up here starting in which digit? We start with the least significant digit, right? And now we're going to split it into groups of 3. And then we can, in our head, you should see the 1, 2, 4 sitting on top of each one of these. Right? You understand? And I can come over here if you can't see in your head, you can come up here and you can complete the group of 3 up there if you want to. Because I can add as many zeros on the left of the number and it don't change the weight of the number, right? So this will be a what? 1. This will be a 2 and a 1. That would give me what? 3. This would be what? 2, 7, 2, 5. And then I'm going to put the little 8 down there so you know because that number would be legal in decimal. That combination of digits would be legal in decimal. It would be legal in hexadecimal. It would be legal in octal. But the problem is every one of them would have a different weight, right? You understand? So is that hard?
Yeah, I know. We have a chart for that.
Yeah, it's over there on the left. very bottom left on the front.
Powers of eight.
There's no chart on the groups of threes, I don't think. But you shouldn't need it, guys. Understand, it's just a 1, 2. Can everybody add 1 plus 2 plus 4 plus 2 plus 1? Okay. So what, if I come over here on every one of these and I put 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4, then that would be a 1, 2, 4. What would this be? 1. This would be a 1 and a 2. What's that equal to? 3. That would be a what? A 2. That would be a 1 plus a 2 plus a 4. What's that? 7. This would be a 2. This would be a 1 plus 0 plus 4. What's that? That's a 5.
Okay, how did 1 and 4?
Huh?
How did 1 and 4?
I don't know what you're at.
The 1, 0, 1, yeah, 4, 2,
This is the binary that it would represent. Just for this. This is just for these 3 bits. We're not going 1, 2, 4, 8, 16, 32, 64 anymore. All we're concerned with is just those 3 little bits. And how would those 3, if I was using binary, how would it go? 3 bits would be what? First one would be 1. So we could do the same thing in hexadecimal. So if I was going to do hexadecimal, then I would come up here and I would divide it into groups of 4. 1, 2, 3, 4, 1, 2, 3, 4. But what I'm looking at is I'm looking at 1, 2, 4, and what would be this one? 8. Okay, so that means this would go 1, 2, 4, 8. And you'd say, okay, that's 8 plus 4 is 12 plus 1 would be what? 13. But you can't write down a 13 right there. You would have to know that that's equal to a what? That that's equal to a D.
Okay.
So on hex, you could use 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4. And you don't have to memorize all those powers of 2s. So you don't have to go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, right? 1024, 2048. You don't have to know all those powers of 2. Because hexadecimal, we're just dealing with 4 digits. And we go what? 1, 2, 4, 8. Then the next one we do what? 1, 2, 4, 8. But the problem is you can't say 8 plus 4, right? It's 12 plus 1 is 13 and write a 13 down there. Because there's no such thing as a 13 in hexadecimal. Well, that's not true. I could put 13, but that's going to represent 16 to the 0, 16 to the first. It's not going to be a decimal 13, right? You understand? So octal is a little easier because now I'm only dealing with what? 3 digits, and you don't have any A, B, C's, D's, E's, and F's up there. It's going to be numbers from 0 to 7. So you don't have to remember that 13 is equal to a D. Can you see that? And if I was going to come up here, and if I was going to take this number and convert it back into, if I got this, if I was going to take this number and convert it from octal 17362 then what would I use? I would use groups of 3s. I would say that's a 1, that would be a 7, that would be a 3, that would be a 6. Oops, I'm thinking hexadecimal, guys. This would be a 6, and that right there would be a 2.
Let that counting sink in.
010 would be 2, 011 would be 3. Yeah, but
You gotta commit that to them.
yeah, and what you're talking about, guys, is you're talking about, and this is what I bring up, is that back in elementary school, you had to learn multiplication tables. And what did you do? How did you learn your multiplication table? to prevent from having to do all that adding.
Study the chart.
You study the chart, right? But after you learn that chart, then it makes multiplication easy. So here on hexadecimal, you got 16 patterns you got to learn. And once you learn that 16 patterns, you can go between binary and hex and binary with not even thinking about it. It just moves, understand what we're saying. 16 patterns. In optical, all you got is 8 patterns that you would have to learn. So you see me, it looks very impressive, but it's not. Right? It was harder for me to learn those multiplication tables than it was a lot harder than to learn this. And if you're going to deal with computers, you're going to deal with these bases. So we're not going to deal with them much in this class, but once you get into advanced PLCs and you start doing logic and stuff like that, you're going to have to know binary. And if you're in networking, if you're trying to figure out this thing called a subnet mask, guys, you've got to know binary. And you've got to know how to take your IP address and convert it into binary, and also take that and figure out a subnet mask. Most of y'all let the computer do that for you. So if you're going to deal with computers, then these guys, from a technical, instead of from a user standpoint of view, you don't care how your cell phone works. All you know is you come up and you type a number, right? Understand that? But if you want to understand how the thing works, then you're going to have to understand these numbers. I think I showed y'all the system information about all the addresses and everything in here, and they gave us the computer displayed it in hexadecimal, right? So hexadecimal is the predominant number system we use now, but octal is still popular in PLC because you have a lot of people that's been dealing with PLCs, and this is the number system they know. And I'll show y'all. So if you take advanced PLC class, we'll show you how you can specify a number. By default, the PLC is going to assume the number to be in decimal, and it'll go through all the conversion to get it back into binary. Are we okay? Questions? Yes. But nobody did this. Okay, let's take a break, guys. 2 minutes.
It's just getting used to this. I think the office. Did you take attendance?
Yes, I did. I do attendance at first class.
Yeah,
So if you came in late, you need to let me know you're here.
I'm here, but I ain't gonna say I was late, because I probably was like 6. It's different if you like 20 minutes. 6 minutes. I was getting out the interstate. How long was it? I was here when you started your presentation with the answers to the quiz. I was say I was late.
Class starts at.
I ain't seen you said late. That was vacation.
Oh,
Yeah,
this is the right class.
that's the wrong place. You're essential.
Would surprise me.
Vacation. I ain't seen you said late.
Here we go. Makes sense.
You went in the last 2 classes? I'm here.
You're here, right?
Oh, yesterday,
Terrence is not here.
I want to know what.
right.
Allison. There's me.
Allison, I'm gonna have to learn you. You're right, right?
Yeah.
I gave us a lab. Taking that tip.
Just to be down there. Well, I don't know. AC. We're gonna go down there today. Hopefully it's still down there. So the last hour in class, we'll go down there and try to finish that lab up. So y'all don't let me forget. I'll have to run off another one. Maybe I got an answer.
On my test rate. When I looked at it, I got 41 rate out of those. I think it was out of 52 points.
Well, now it's going to be after 52. And then we're going to add 2 back on there, but one of them was worth 2 points. So that'll be 3 more points we add back on.
So we get still, it was like 49, 52 to 40 still. But anyway, I looked at it, it's like at 75.
Well, the problem is that it ended up being the same because when I set the test up, I didn't take off the scale from the last time the test had been offered. So the scale came up to be the same. Some of the questions were down as bonus questions, but they wasn't really bonuses because it didn't meet the criteria. So what I did is I went out and cleared all of it out, and then I redid it. So does that make sense?
Yeah, it's like a little.
Even with all these added back on. So we're gonna drop 43. So that'll make it one less under, and then we're gonna add 35. I think that was worth 2 points, and 39. I think it was worth 1 point, if I remember right. So I don't know what is possible, but I have to go back and move it. I don't know.
Yeah, that was one. Alright.
Yeah, and originally it was displayed in points. I like to take that off, make it do it in percentage because that makes more sense. So this is not going to be on the slides on Blackboard. I just added it. I realized there was nothing in here that I actually did this. So the number of possible numerical combinations can be calculated by raising the base to the number of digits, right? In fact, I need a raising D. The number of possible numerical combinations. Of course, here you're starting with 0. All we do is do what? Take the base and raise it to the number of digits. The largest possible number is the base raised to the number of digits minus 1. You okay there? So that's our numbering system. So what number systems did we look at? We looked at decimal, right? We looked at binary, hexadecimal, and octal. But we got to understand that the computer has to deal with other things besides numbers, right? So a code is a system of words, letters, figures, or other symbols substituted for other words, letters, and figures. Codes most often used in PLCs is the binary code, binary coded decimal, the gray code, the one we've already played around with, American Standard Code for Information Interchange. The book talks about ETCDEC, which is Extended Binary Coded Decimal Interchange Code. This is wrong. It's not known as extended. I should have wrote that down. This is wrong. The book says it's also known as extended ASCII. That is false. And then a new code. Well, it's not a new code. It's been around for a few years. It's called Unicode. And this is for internet. And also, most of your word processors and stuff like that use Unicode. Are we okay? Yes, no? I don't think the book talks about Unicode. I'll show it. So 10 combinations used in binary. So the decimal number system has how many combinations per digit? 10. Right. So if I was going to use those 10 combinations with binary, that would be a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, and a 9, and then I would be through. The problem is how many combinations can we represent? We can represent 16 combinations with 4 bits of binary. If I use binary to directly represent decimal, we sacrifice 6 combinations. Right? Everybody understand that? So that's what we do with BCD. BCD stands for binary, and what's the second word? Coded decimal. This is not a numbering system. It is a code. Code is when we use something to directly represent something else, right? So what we do is kind of like hexadecimal. We split it up in groups of 4. 4 bits representing 10, 11, 12, and 15 are what? Not valid. Only 4-bit patterns representing digits 0 to 9 are valid. So this would be BCD. This is not hexadecimal. It does not go 1, 2, 4, 8, 16, 32. Each one of these 4-bit patterns directly represents a decimal number. This is not a weighted numbering system. It is a code. You cannot go from decimal to binary doing this way. So this is the way I would come up here if I was going to represent a decimal number in binary. And I don't know what to do about this, guys. Somebody in this class is going to do this. They're going to try to go directly from decimal to binary by using BCD. You cannot do that. Wow. So if I had a decimal number, 9,684, and I wanted to, how would I convert that to binary? I would start out by laying out a chart, right? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024, 2,048, 4,096, 8,192, 16,384. And then I would start doing what? Subtracting. So that's one way we would go from decimal to binary by subtracting the decimal equivalents of powers of 2, right? Everybody okay? Now, if I was going to go from base 10 to BCD, I would come down here and I'd write down the binary pattern for a 9. I would write down the binary pattern for a 6. I would write down the binary pattern for an 8. And I would write down the binary pattern for a 4. This is BCD. This is not weighted. It does not go 1, 2, 4, 8. So if I came up here and said 1, 2, 4, 8, 16, 32 and converted that to decimal, you would not come up and get 9,684. This is not a weighted numbering system. This is a code. You cannot go between decimal and binary by using these groups of 4s. And I didn't put base 2 out there. I put what? BCD. This is not a weighted number. It is a code. And you can do math with this if you figure it out. But I'm not going to show y'all that. Because it takes some compensation. So the computer has to deal with this a lot because the computer has to represent decimal numbers a lot, right? Binary coded decimal. So let's make up a number, not that big. This is not a weighted number system. It is a code. If I'm going between decimal and binary, I have to subtract powers of 2s. Here, I'm going to just represent patterns. And they're the first 10 patterns of the hexadecimal. If you look at your BCD, it says yes, 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 yes. And then what it says on the last 6, it says no, 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 right? You'll see that on the right-hand side. This is not a weighted number system, it's a code. Is somebody in this class going to go between decimal and think they're going to binary, instead go to BCD? Is somebody in this class going to do that? Yes. And I don't know what to do about that. I wish there was. This is base 10. So let's take that to BCD. And you have to use, it's a code, so you don't drop leading zeros. The leading zeros are required because it's a code. So what would be the code for a 6? 0 is 110. What would be the code for an 8? No, 1000. 1000 is a decimal number. What would be the code for a 5? And then this would be what? BCD. It is not a weighted number, it is a code. So the computer could not do math with this. It could not add, could not do that. So before it did math, it would have to do what? It would have to convert it into true binary and then do binary math. It's a benefit for you because you can go between, you understand this number, BCD. You understand it, so because it's so similar to the what numbering system, the decimal numbering system. It's very similar to it, right? And it gives us the ability to represent decimal numbers with 1s and 0s. But the computer would have to convert this to binary if it wanted to do mathing. But luckily, computers have the ability to process. So I could come up with an algorithm. You know what an algorithm is? Anybody know what an algorithm is? Well, it's a step-by-step process to solve a problem. So a recipe is an algorithm. If you follow a recipe. So I could come up with an algorithm that takes this, does some patterns, adds 9, does this, and then I could convert that to binary. I could do math with it, and then I could come up with an algorithm that converts it back to BCD so I could display that information. So basically, when you type in your PLC, when you're setting up a counter, you put 137 seconds, that's BCD, or some code that represents that. But the PLC, the inside the computer, is going to have to do something to get it to binary to make that work, right? But an algorithm programs, and like I told y'all guys, when I first got into microprocessors, there's only 2 operations that processor could do. It could add and it could subtract. But if you could figure out the sequence, you could write a program that did square roots. You could write a program that multiplied. You could write a program to divide. Now, over time, they've added those instructions to the instruction set. So there's some BCD instructions now that gives us the ability to do that. But you need to understand the difference between binary and BCD. BCD is not a numbering system, it's a what? It's a code. But it makes it a lot easier for us to understand it, right? You understand? So yeah, the microprocessor deals with these things now. They can deal with it directly. but originally it was all binary. So if I wanted to enter BCD, if I wanted to go ASCII, so I'm typing on something like a keyboard, it's sending me a binary code that represents the number 1. I had to figure that out and get a weighted number 1, right? You understand to do math. So ASCII is a code. And it's a binary code. But we use hexadecimal a lot because we can go between those spaces real easy, right? Or we should be able to. So this is counting in binary. 0, 1, 2, 3, 4, 5. I think we go all the way up to 63. And notice all the even numbers. This bit right here is a what? 0. All odd numbers. This bit right here is a what? 1. So that's what I'm telling you. You know, if you're doing a worksheet or something, you start off with an odd decimal number and you end up with an even binary number, what do you know? You know it's wrong. If you start off with an odd number and end up with an odd binary number, it might not be right, but at least it has a chance to be right. How did I get here, guys? I think my thing shifted around. I actually got an extra number in there. Here we go. BCD is not a numbering system, it's a code. Convert a number from any numbering system besides decimal to BCD. The number must first be converted to decimal. Then represent each decimal digit with a 4-bit BCD code. Everybody okay? Yes, no? So decimal to binary, we okay there? Anybody got any problem there? Yes or no? Gray code. Gray code. The problem we have with binary, and I'll show y'all this. It's back here again. Sorry, guys. So if I was going to count in binary, how would the count go? So this is counting in binary. The chart only goes up to 63. So I want to go from 0, just look at the binary, don't look at the decimal. So I want to go from 0 to 1, how many bits change? Okay, so here we had a 1-bit change. Let's do this another color. When I went from a 1 to a 2, how many bits changed? 2. When I went from a 2 to a 3, how many bits changed? Yeah, just this guy right here. See, this was originally a 0, so we had a 1-bit change. When I went from a 3 to a 4, how many bits changed? This one, yeah, 3 changed. 3, Rich. When I went from a 3 to a 5, yeah, when I went from a 4 to a 5, how many changed? 1. When I went from a 5 to a 6, how many changed? 2. And then when I went from a 6 to a 7, how many changed? Just 1. This guy right here. Yeah. We okay? Then I went from a 7 to an 8, how many changed? Yeah. So what you can see, when I'm counting in binary, a different number of bits change each time. In digital, we have something we call a propagation delay. A propagation delay is how long it takes a signal to move through a digital circuit. So what we're saying is the more bits I change, the longer it would take the counter to count and get the count through. And if we get into high-speed applications like digital encoders on a motor, which is sending out a sequence of pulses, we could very easily exceed what our counters can do. So what they did is they came out with a code called a gray code. This is counting in gray code. This is a code, guys. This is a code. So it takes a little while to figure this out, but this is counting. So this would be a gray code for a 0. This would be a gray code for a 1. This would be a gray code for a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I can keep going, 15. But let's just go this way. So here's the gray code. Here's the gray code for a 0. How many bits changed? Well, we started here. So how many bits changed between a 0 and a 1? 1. How many bits changed between a 0 and a 2? No. This guy was already a 1. This guy so that was already a 1. So this guy changed. So going from a 2 to 3, how many changed? 1, right? Going from a 3 to a 4, how many changed? 1. Going from a 4 to a 5, how many changed? 1. So you notice for every count, it only changes what? 1 bit. Even when I go backwards, so if I go from a 6 to a 5, it only changes 1. So no matter which direction I'm counting in, 1 bit only changes each time. So what means, instead of me trying to propagate all these counts through these counters, we're only dealing with one propagation delay of 1 count. So these guys are used for extremely high speed counters. The problem is, how do I get this back to the decimal equivalent? I know this pattern right here equals to 14, but I can't use the 1, 2, 4, 8, 16 code anymore. It don't come out right. It is not a numbering system. It is a code. But computers love this stuff. They love this stuff. Programmers love this kind of stuff. So they figure out how to change it over, right, to do the math. And it's not easy. Well, it is once you understand the feature of how it works. It's hard to learn. So I think which one in your lab on the number system, you got 1 gray code on that thing. So which number is that one? And this is the last time you're going to see this, but you need to understand the gray code, right? Understand. It's just a watch. It's a high-speed counting code. So on your work, it should be one that you had to do that wanted you to convert the gray code into decimal.
Well, you got gray code at
Okay, but gray code, so first of all, we'll go to binary, and then we'll go from binary to hex, right? How many of y'all got that? So this is the process. So what's the gray code? So what would be, so it's the hexadecimal? So what's the gray code? Start with the left digit.
1,000. Okay, 1, 0, 0.
So if you don't get this, don't worry about it. So this is not a code. This is gray code. So let's put it right. That's not a number system. So this is what we have to do. So we'll call this G, and then we'll call our answer B. And I'm sorry. So let's say if I come up with a 0, if I come up with a, we're going to do what we call an exclusive OR. So a 0, 0 would give us a 1. A 1, 0 would give us a 0. A 0, 1 would give us a 0. And a 1, 1 would give us a 1. So first thing I do is I bring this bit down. Then I exclusive OR this one. And then I'm going to write that number down. What would that be? So I'm going to look at my chart. So I'm going to say a 1 and a 0 would give me a what? Oh, I got this backwards, guys. Sorry. I gave you all exclusive NOR. So this would be a 1 and 0. What would I get? A 1. This would be a 1 and a 0. I'd get a what? A 1. You'll see what I'm doing? So I'm taking this one in exclusive order with that one. Then I'd take a 1. Then I'd say, okay, a 1 and a 0 would give me a what? 1. A 1 and a 1 would give me a what? 0. Then I would say a 0 and a 0 would give me a what? 0. And a 0 and a 0 would give me a 0. And a 0 and a 1 would give me a what? And then that would be the binary number that this would represent. So now what I would do is I would take this and split it into a numbering system called hex, if that's what they want. So that would be F1. And this would be the decimal way. Now this is what I'm not this is not what I don't know what they're looking for, right? You understand what I'm saying? So this could be 8-9, but that would be 16-bit gray code. But F1 would actually be the weight of the number. Well, I'm not sure what the author's looking for. If I go from gray code to hexadecimal gray code, then it would be 89. If I go from gray code to hexadecimal, then it would be F1. So we're gonna throw that one out, but I'm gonna just show y'all. So that one's not gonna count. I don't even think the book, what's the problem? Have y'all been through the chapter? Is gray code even in the book?
Yeah.
It is.
Yeah, but it's got some blank pages.
It's got blank pages.
Well, no, it's got some verbiage where it's just.
They don't got none of that.
I'm looking at Gilhard Wilson.
Oh, I don't know. What's that?
Oh, we don't got none else.
Yeah, that's what I'm saying. That's the problem. So 89's not in there. 89 is not in there.
Okay.
Let's make sure we did this right. So we bring this one down, then we exclusive forward this with this. So that'd be 1 and a 0, which would give us a what? A 1. This would be a 1 and a 0. This would be a 1 and a 0. This would be a 1 and a 1. This would be a 0 and a 0. This would be a 0 and a 0. So this is right. So the book don't even have.
They do by themselves.
What's that?
You do the 1 0 0 0 and 1 0 0 1 by itself instead of doing them all together.
No, you got to do the whole code. I mean, you got to. Huh? Yeah, but you can't do that on a gray code. So the book don't do the gray code right. So this would be the actual count. They don't split it up into 4-bit groups. This would actually be the actual count, and this would be the binary number it represents. So you're saying they split it between 4 bits and 4 bits?
Yeah, if you did that, FB would be the answer.
Yeah, but that's not the way gray code works. Huh?
Yeah, I mean, don't worry about it.
Yeah, this would be the two possible answers. Gray code, if I was going to do gray code, so what the author did is he treated this as a different number and this is a different number, which would give the number the wrong weight, right? You understand?
That's how all of them do it.
Just gray code. That's only, there's multiple gray code on there?
Yeah, it's one, it's five of them you convert from gray code to hex.
5 questions? So what we're going to do is we're just going to mark that off. It looks like even the author, because he didn't do it right. What he did is he took this number, which is the number, and from what I understand, he did it like this, and then he did it like that, like it was 2 different numbers. That's the way this guy did. But you don't split up a number, right?
That's how all of them do it.
Well, then he did every one of them. Well, odds are if you did one of them wrong, you did all of them wrong.
Oh yeah, you got it.
So if we can prove that, Notice if I was gonna do that, I would split this in two, but we could come up here and do that. So according to mine, this should have a decimal weight of 15. Because I started at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if I was to come over here, that means I better come up and get 15 and not splitting them into groups of twos, right? So 15 would be a 0, 1, 0, 0. So what would I do first? I'm sorry, one more 0, 3, 0, 3. So if this converts over, if I was to split this up, you'll see it's going that. If I was to split this up, then that I couldn't do it, right? You understand? So let's do that. So I bring this one down. That would be a what? 0. And then I'm gonna come over and exclude it over this and this. What's that? A 1. And that's gonna be this and this. That's a 1. This and this would give me a 1. That and that would give me a 1. I convert this over to decimal 1, 2, 4, 8. That's gonna be equal to 15. So the guy, the author of the book, made a mistake. He don't know how to do gray code. Well, he does, but he treated it like a hexadecimal number instead of a number, right? Y'all understand what I'm saying?
I'm gonna do a great hex conversion.
Yeah, you can look at a table, but if you look it up, they'll show you this. I didn't have time to go from binary to gray code. Binary to gray code is a little different. You start off by bringing it down, and then you exclude it or from left to right. But going from gray code to binary, you go up and do this stuff like that. Y'all need to know how to do this? No, not for this class. So all the ones about gray code, what am I gonna do? I'm gonna take them off.
Thank
Sure, we can. So if I kept counting, 8, this would be 15, 16, 17, 18, 19, 20, 21, 22, 23, and then 24, 25, 26, 27, 28, 29, 30, 31. And you can't use that thing about your odd numbers having this, right? I'm saying, because this is a code. This is not a number system, it's a code. So which one y'all want to go to, over to the decimal and see if it works out right? 29? 1, 0, 1, 1, 1. So what I do first? Drop the 1. Then I left my, let's write our chart back over here. So make sure. Y'all got it? Do I need it right over there? You okay? We're going to see if this comes up to be, which one am I using? 29? Okay. So 0, 0 should give me a what? 0, a 1, 0. Let's do that. Yeah, 1, 0 will give me a 1. A 0, 1 would give me a 1. And a 1, 1 would give me a 0. So we'll go over here. We start off with a 1. Then I go this to this. What would that give me? And then I go what? So 1, 2, 4, 8, 16. So it's going to be 16 plus 8 plus 1. Hopefully we did that right. What would that be equal to? I think we might have did. We do that right. Huh?
you.
1, 2, 4, 8. I'm sorry. 1, 2, 4, 8, 16. Right. 1, 2, 4, 8, 16. 1, 2, 4, 8, 16. 16 plus 8 plus 2. I'm sorry. I can't do math. So what does that give us? Is that what we started off with? Let's go back and double check it. Did we do that right?
What happened to one? It's 1, 2, 8, 1, 2, 4, 8, 6,
30. 10111. Okay. We're spending too much time on this one for something that we're not going to be responsible for. So what do? We start off by doing what? Okay, drop this down, right? And we take this and this. What would that give me? Okay, be a 1. 1, 1 would be 0. It would be 1. 0. Yeah, we're doing something wrong. Did I miss a count over here? We're coming up with this one instead of this one.
That's not even using.
That's right. Go back. Okay.
Yeah, that's not you using.
I'm using this one right here.
I thought we were trying to get 29.
Yeah, we're trying to get 29, but we're not getting 29.
29 is what? Like 9?
You trying to get 29 out of 29?
2, 8.
So this is supposed to give me the actual number. And what we end up with is 1, 2, 4, 8. 1, 2, 4, 8, 16, right? That'd be 16 and 18. And I know we got a problem already. Why do I know we got a problem already? Yeah, we ended up with an even binary number. We ended up with an even binary number. We started off with, we know the number's odd. We don't know this number's odd because it's a code, right? But we know this, we know the number that it represents. So I'll have to figure it out, guys. Y'all don't worry about it. Alphanumeric code represents, you can use alphanumeric code to represent what? Letters, decimal numbers, and special symbols. And what was the first code, or what was the first alphanumeric code we looked at? The American Standard Code for Information Interchange, or most people call this ASCII. It's a 7-bit code which gives us 128 combinations, right? Data is often sent in bytes. The 8-bit is the 8-bit and 1 byte of transmitted data usually used for parity, and most often given in hexadecimal. So your charts are usually set up in hexadecimal because they're so much easier to deal with in the binary code, right? I think this is pretty close to the ASCII code chart that I gave y'all out. First 2 columns, we call these control codes. So this is what the devices can, we call them handshake, software handshake. So before we transmit data, we need to have first a method of being able to say, okay, if the data is okay, plus to be able to do things like beep or beep. So we used to ding every time we did a carriage or something. Backspace, DS, that would be the code for a backspace. LF would be the code for a line feed. You can still see this sometimes, guys. It'll pop up and you'll see on the internet when you look at something, it'll have these percent signs and then it'll have a 20 out there. Well, that's the code for a line feed. So sometimes you'll actually see this pop up. A vertical tab, form feed, carriage return. These are 2 important ones, acknowledge and not acknowledge. So this is used a lot where I'll send an information to a device and then it would check the parity of the device. And if it was okay, it would send back an acknowledge, and that would tell the transmitter that it could send another byte, right? If it came back and sent back a not acknowledge, then it would tell my transmitter to resend the last one. So these are all control codes right here. And this is where we get into the alphanumeric code. So 20 would be the code, I'm sorry, 20 is another control code. ST, what do you think that stands for? what do we put between words? So see if y'all can do y'all's first name in ASCII code. Y'all can use text. So what would mine be? So uppercase R, what would I use? 5.2. And then lowercase I, what would I use? 6.9. Now y'all got the code, right? Then lowercase c, I would use what? 6.3. And then lowercase h, lowercase h, I would use
6.8.
Now the actual code would be 52, right? I understand, but it makes it a little easier to do it in hexadecimal. So it's not column 5, row 2, right? And of course, here's the code. I use this a lot. You press button, you press your delete key on the calculator. On the keyboard. And these are the codes. These are the actual control codes. This is the book. I don't know what table this is. The B, L, bell, backspace, horizontal tab, line C, vertical tab, forward C, carries the turn, shift out and shift in. I've never seen this used. Data link escape. The DC codes, these are usually user definable, so the two pieces of equipment establish that. Not acknowledge, cancel. Okay there. This is actually extended ASCII. So this turned out to be an 8-bit code. You can see what they did. They added a bunch of what to this. Yeah, symbols. Of course, it still doesn't use the symbols that we use now. In fact, most of us, used to a long time ago. If we wanted to send somebody a smile, what would we use? We called them emoticons. What did we use? Y'all remember? Yeah, semicolon and then a parenthesis. Of course, now we use these emojis, which are emoticons, and those have got to be represented with codes, right? You understand that? So using even extended ASCII, we've got some features of stuff that we can use. You can still get to these guys. Unfortunately, I'll try to get my other computer in here and show you how you can get these codes. Because these are not on the keyboard, but they're available. And I'll bring my other computer in the next class and show y'all how you can get to these guys, all the guys. One thing they added that was great for us is they added micro and omega. So up until they added these, anytime we wanted to put ohms, we had to spell out ohms. But when they came out with enhanced ASCII, EA is what? That's for ohms. And that would be a decimal 234. 236 was infinity. We use that every once in a while, and micros on here somewhere. 230. You have to know these? No, because what would happen, I dealt with ASCII for a long time and I learned a bunch of the codes, but just like I did hexadecimal, but most of the time when you go to codes, you're going to look up the numbers and stuff on a chart, right? Does that make sense? I remember what the chart's at. Well, you don't even need to remember that. I mean, even if you don't have a chart, you can go to the internet up there, type in ASCII code, click on images, and it'll bring you all kind of charts up there that you can get in. Oh, here's pi. We use that a lot. So first of all, we had to type all this in, but I'll show you how you can still get to these codes. They're still there. This is a legacy code used by IBM for mainframes, I don't know of any current PLCs that use EPSODEC. It's an 8-bit code which gives us 256 combinations. And then I think there might be an EPSODEC code in your book. But we're not gonna see this. This is not used by any PLCs that I know of. But it was originally used by mainframes. This was one of the first codes that they came up with to represent letters. This is EPSODEC part. Looks like it's missing something. This is not out of y'all's book. Do y'all have an EPSODEC chart in y'all's book? That don't make any difference. Unicode. This is the guy now, guys. This is the guy. We have what you call a universal text format. We have a Unicode 8, we have a Unicode 16, and a Unicode 32. This is the one that's predominantly used by the internet. So normally we type this in, so I'm going to come over here and I'm going to say I want to insert, and I'm going to insert a symbol. And what code is it using? Unicode. And what base is it using to display it for? And if you notice, if you look, so what's the ASCII code for the number 1? 3-1. Well, even Unicode, they've kept the ASCII code. Do that. So the lower 8 bits is still the 7-bit ASCII code. But what they've done away with is they've done away with the enhanced ASCII because they needed more stuff to do. And you can see what's nice about Unicode. How many characters can I represent with 4 hex digits? 16 to the 4? 65,536, which is basically every modern language that's out there. So now we not only can represent the Latin alphabet, we can also represent other. So originally when the internet came out, guys, everything was English because the only code available was ASCII. That was the code the internet uses. But over time, the internet has adopted Unicode that gives them the ability to do what? So even here, this don't give me all 65,536 combinations, but look at all the characters and stuff we can represent now. And even your emojis, it's not in this chart, but even your emojis is a Unicode. You know, they standardize those, right? You understand that? And it's a 16-bit code. So not only can they do that, this kind of has it. That's a little smiley face, 263A. But now, not only do we have little smiley faces, now we have smiley faces that are they use gradients to make them look 3D, and they have them crying and smiling and all that. But everything you do has to be represented with a what? With a code, yeah. And sometimes they'll send you one of those emojicons, and you don't have that is not installed on yours. You ever seen that? And you don't get it, or you get something different. So this is Unicode. The internet uses this. Your cell phones use this. And you can see we got just this, and they don't put all 65,536. So sometimes you'll go to a website and it'll tell you you need to download the code set. I don't know if you've ever seen that before. So they don't put all 65,536. These are wingdings, which is basically most of your extended ASCII. Unicode goes all the way up to a 32-bit code, which would give us a lot of, which would give us actually 4,294,696. This is the number, so 2 to the 32nd, this would be the number of characters we could represent. So we don't currently use that. I don't know anybody that uses the Unicode 34, 32. This is the predominant Unicode we use. by the internet, used by all your Microsoft products, used by your cell phones, used by just about everything is using Unicode. And like I said, with 65,530 combinations, we can represent every modern language out there. Plus, we can also add these other codes for these emojis. I think that's. So this is UTF-8. And guys, all I'm just trying to do is just tell you what's going on out there, right? So when you hear these terms, you do what? Yeah. Now when they start throwing out all this stuff, I can't watch shows that's got a lot of technical information on it because most of the time they get it wrong. So that's not right. But sometimes I laugh. Now let's take another 2-minute break. Nobody did it. That finishes this chapter up.